Hello everyone and welcome back to this next lecture. So in the previous lecture I gave an overview of timers, of the three timers which are present in the F28069 and how these timers work, the fact that you can load a period value into their registers and you can also load an optional prescale value so that you can actually increase the time period that you can configure. And at the same time we also saw the control register, the fact that you can start and stop as you want, and you can also enable interrupts. Now, as you can already guess, the entire or rather the final result of a timer is to produce an interrupt when the timer counts to 0, because that's exactly what we're trying to do. We are trying to set a time period and generate signals each time the time expires. This is just like how we would use a stopwatch or how we would place an alarm or we configure an alarm on our mobile phones. So here, of course, the question then is, what about these interrupts, right? We saw that in the previous lecture that there is a TIE bit on the timer control register, which if it is set, then an interrupt will be issued when the timer counter reaches 0, decrements to 0. Now, in this lecture, I'm going to talk about the significance of interrupts and how interrupts are handled by the F28069 processor. So, just another brief background that there are two ways in which the processor can communicate with peripherals, right? So one possible way is that the processor can continuously keep pinging all the peripherals, asking them if there is any event or data that needs to be processed by the processor, right? So in this case, it is the processor that goes to the peripherals. Now, the problem is when you have a large number of peripherals, and that is the case with a processor like microcontroller like the F28069 and most other modern microcontrollers, it will be very inefficient if you are asking the processor to go around pinging the peripherals. Because remember, the processor also has to be executing instructions. That is the main objective of the processor, to actually process data, right? You wanted to run control algorithms, we wanted to do PI control, phase lock loop, all kinds of things. And those things also require time and also resources. So you can't be expecting the processor to at the same time also be asking the peripherals if they have any data or event that needs to be processed. Now, the concept of an interrupt is that this reverses the communication process. Now it is the peripherals that are reaching out to the processor. The processor can just keep doing what it's doing, right? When the peripherals have any event or data that needs to be handled by the processor, only then will the peripheral reach out to the processor. So this way the processor can stay focused on executing instructions and executing control loops and things like that. And it can only communicate with the peripheral when there is a need to do so. When the peripheral asks the processor that, look, I have something for you, right? Only then can the processor actually deviate from the task that it is performing. And another major advantage of this process, at least this approach, is that now the processor can handle multiple requests from different peripherals. So let's say, for example, you have 4 different peripherals which are active in your microcontroller for various reasons. Let's say, for example, you're doing ADC, you're doing EPWM, you're doing timers, maybe even something else, right? All these are generating interrupts. They all are producing data. They are all producing events. Now the question is, instead of the processor going out to them, if they reach out to the processor can handle priority, assign priority to the different interrupts and say, okay, the PWM is high priority or ADC is high priority, timers are low priority, things like that. So these things can be assigned priority by the processor so that it can actually handle interrupts in a better manner. Now let's go into the details. Now, here I'm going to make a little statement that understanding how interrupts are set up, how they are serviced by the processor, how they are completed, and how they need to be cleaned up can be very tricky. Alright? And especially if the peripheral has a lot of configuration options. Now, the timer does not have a lot of configuration options, and that is one of the reasons why I'm starting with the timer. Other peripherals like EPWMs and ADCs have a lot of configuration options, and therefore it's going to be much more tricky with those peripherals, right? Now, another thing is some peripherals can generate a number of interrupts for various reasons and even at various times, right? Like the EPWM can generate a number of interrupts. EPWMs, ADCs, they can generate a number of interrupts under different conditions, and therefore you can also schedule them at various times. In comparison to that, the timers are actually a little simpler. When they count down to 0, they generate an interrupt. That's it. Now, remember that the F28069 is actually a full-fledged microcontroller that can actually handle a lot of cases in industry, right? It handles a lot of industrial applications. So it has a very large number of peripherals. And each peripheral can actually issue a number of interrupts. It's not just one interrupt, it's actually a number of interrupts. And therefore, because of all this, the entire number of interrupts, the sum total of interrupts that the processor will need to handle is very large. So therefore, the processor cannot handle all these interrupts alone. And therefore, the processor delegates this to what is called as a Peripheral Interrupt Expansion Module, or PIE module, right? So this PIE module is merely a delegate which handles these interrupts from all the processors and just filters them so that the processor does not have to bother too much with how to handle all these. So this Peripheral Interrupt Expansion Module, or PIE module, simply collects all the interrupts from all the peripherals and passes them on to the processor through some kind of sequencing and priority. Now, it's important to remember some interrupts will go directly to the processor. We have already seen this, right? CPU timer 1 and CPU timer 2 will generate interrupts T×1 and T×2 which are fed directly to the processor. They don't go through the Peripheral Interrupt Expansion Module. The interrupt from CPU timer 0, that is T×0, that does go through the PIE module. So this again you have to look into. It all depends on the microcontroller. If you're using another family, things may be completely different, right? Each microcontroller is designed differently, and the purpose behind all this is known only to the engineers at Texas Instruments, right? So let's keep going. So this is a block diagram of the Peripheral Interrupt Expansion block. Now, the F28069 can handle up to 96 interrupts altogether from all different peripherals and everything, including even the interrupts which are passed directly through it. Now, these 96 interrupts are handled by the PIE module. Right? Now, for example, if you see, I'll show you in detail, but you'll see 96 interrupts are handled by the PIE module. Altogether, there are 12 groups of interrupts in the PIE module. So this PIE module, again, because it's 96, and it's whenever you see any large number in microcontrollers, it is common that they break it up into segments, because otherwise it becomes very difficult to deal with them, right? Because remember, the F28069 is a 32-bit microcontroller, and most registers are either 16-bit or 32-bit. So if you were to handle 96 interrupts, obviously you would need many registers. So this automatically implies that you have to break it up into groups. So there are 12 groups of interrupts in the PIE module, and each group has up to 8 interrupts, right? And these 8 interrupts come from different peripherals. So the final result is that each group produces one interrupt that goes to the processor. And these interrupt signals are int1 to int12, right? And as you might have seen, CPU timer 1 and CPU timer 2 produce int13 and int14. So that's not a part of this PIE module, right? So the PIE module then passes on these 12 interrupts, which are then handled by the processor, along with those which are handled separately. Now, the rest of this discussion is going to be a little complicated, So you might have to watch this video twice, right? But make sure you understand this. There are 12 groups altogether. And each group has 8 interrupts, up to 8 interrupts, because remember, some are not even used, right? Some are not used. We've already seen that with the GPIO pins. Some GPIO pins were not assigned any functionality, right? Now, in the same way, some interrupts will also not be used. Now, let's keep going. How does it all work? The flow. Now, as always, the communication starts from the peripheral that reaches out to the processor. So, it all starts with the peripheral. So, a peripheral generates an interrupt. And this is only possible if interrupts are enabled at the peripheral. Now, we've already seen this with the timers. There is a TIE bit in the timer control register. Only if that bit is set is an interrupt issued. If the bit is reset at 0, it will not create an interrupt, even if the timer goes to 0. The timer keep on running, doesn't matter. No interrupt will be generated unless the TIE bit is set to 1. Now, if interrupts are enabled, then this peripheral which generates an interrupt is fed to one of the groups. Okay. Now, I'll talk about this very soon. There is a map, and the peripheral, each peripheral is assigned a group. So, it is fed to one of the groups, right? Now, once it is fed to the group, a flag will be set in that group for the interrupt from that peripheral, right? And this is done in a register called as the peripheral interrupt flag register. And if the group is X, let's say it's group X, let's say group 5, then in that case, there will be a peripheral interrupt register number 5. So this will be PIE IFR 5, right? For every group, there is a peripheral interrupt flag register. And in that flag register, there will be an interrupt, there will be a flag set for that particular interrupt from the peripheral. Again, an entire map exists. I'll talk about that very soon. But for now, you just have to know that every interrupt from every peripheral is assigned a group, and within that group, it is also assigned a particular bit in the flag register. Now, once a flag is set, we still need the interrupts for that peripheral to be enabled in that group, right? We need peripheral interrupts enabled at the peripheral. That's a different matter. But besides that, the interrupts also have to be enabled in that group. And this is done by setting a bit in a register called as the peripheral interrupt enabled register for that particular group. So let's say, for example, we are talking about group number 5. Then in that case, there will be a register PIE IER 5, right? That is PIE, that is the interrupt enabled register for group number 5. And within that, there is a bit corresponding to the interrupt from that peripheral. Again, this entire assignment is already done. It is done for the F28069 and it is done for most processors in the Texas Instruments C2000 series, right? But if the interrupt is not enabled in the group, nothing happens. So even if the peripheral generates an interrupt and it goes to the group and the flag is set, if we do not enable the interrupt in that register corresponding to that group, nothing will happen. However, if we do enable the interrupt in the group, then the PIE module will then check if there is any higher priority interrupt already flagged in the group. Alright, because remember, it's all priority basis. Now, until the interrupt is the highest priority interrupt in the group, the PII module will not do anything with that interrupt. It's just going to wait on the interrupt. All other interrupts will be serviced first. Rather, higher priority interrupts will be serviced first. So it's a kind of a first come first. Actually, it's not a first come first serve basis. It's more like a hospital emergency room, right? The more serious patients will be treated first. That's how it is. If you go to a hospital emergency room, there is no first come first serve basis. The person who is in worst shape will go first, right? Now, if no other high priority interrupt is flagged in that group, then the next thing that the PIE module will do is it will check if the processor is already dealing with an interrupt from that group, right? Why? Because you cannot, there can be only one interrupt from a group at a time. If the processor is already dealing with an interrupt from the group, then it will not pass on the interrupt. And this is done by checking a bit corresponding to that group in a register called as Peripheral Interrupt Expansion Acknowledge Register, PIE ACK. Right? So again, this has a specific structure corresponding to each and every, so every group has a bit in this register. Right? We have already seen there are 12 groups, which means there are 12 bits in this register corresponding to each group. If the processor is already handling an interrupt from the group, then that bit will be set, and in that case again the PIE module will wait. If the processor is not handling another interrupt from the group or is done handling an interrupt from the group, right? Let's say for example it just finished, that's also okay. Then the PIE module will then pass on this interrupt as int x, with x the number of the group. So if you're talking about group number 5, then if the processor is not handling another group from group number 5 and there is no other higher priority interrupt in group number 5, then the PIE module will pass on an interrupt number 5 to the processor. Alright, and at the same time it will set, this will set a flag in the interrupt flag register. This is the global interrupt flag register that is handled by the processor. Now we are no longer talking about the PIE module because now it is moved on, right? The PIE module has passed it on to the processor. So this means that the processor will have a bit set corresponding to that group. Or rather this flag or this register will have a bit set corresponding to that group. Now the processor will check if the interrupt for that group is enabled by checking the corresponding bit in the interrupt enable register. Now let me just go back and show you the block diagram. You saw here we are already at this stage, right? The PIE module is until there, and if it passes it on, let's say interrupt number 5 is somewhere here, then in that case a flag will be set in this interrupt flag register. But that's not enough for it to go on. That interrupt must be enabled in the interrupt enable register. That is, the processor will check if the interrupt for that group is enabled by checking the corresponding bit in the interrupt enable register. Right? So each group has a bit in this interrupt enable register, and you must enable it so that interrupts for that group can be dealt with. If the interrupts for that group are not enabled, the interrupt flag will remain set, but nothing happens. Alright? If the interrupts for that group are enabled, then the next check is if the processor is currently handling another interrupt. And this is done by checking what is called as the interrupt mask bit, INTM. Alright? And if you go back here, you'll see that's what it is. This is the interrupt mask bit. If the interrupt mask bit is 1, then the processor is currently busy with another interrupt, right? Then in that case you must wait. If this process bit is free, then the processor is free, right? And if the processor is free, then it can start. If the processor is free, the next check is if there is a higher priority interrupt flag in the IFR register. Remember, again we are talking about priority. So there is priority within a group, there is priority between groups, right? That's how it is. Now, if no higher priority interrupt is already flagged, then this interrupt is finally ready to be processed. And when it is ready to be processed, the processor will then set this interrupt mask bit to 1. Why? Because this means the processor is now busy handling this interrupt. This is a way of saying, look, I am now busy, right? Now, the processor will then clear the flag corresponding to the interrupt in the IFR register. This the processor will do. Why? Because it has started processing the interrupt. And then the processor will look in the appropriate PIE IFR, that is the PIE interrupt flag register corresponding to the group, because now it knows that an interrupt came from this group. So it's going to look in that group for the corresponding interrupt, the appropriate flag register. Alright? It will clear the flag corresponding to the interrupt. And finally, the processor will then start calculating the address of the interrupt service routine. Because remember, the interrupt means it has to, for the interrupt to be serviced, we need an interrupt service routine, which is a function. And at this time, the processor will save a snapshot of what it was doing in the RAM. So this means some important registers, such as the accumulator and a few others, will be copied to the RAM so that it has a snapshot of what it was doing, right? And then it is now ready to jump to the ISR and do what the interrupt is asking, right? So whatever the interrupt is asking, that is whatever you want from the timer, that is when the timer expires, you want it to execute a control code. So now you have to put that control code in your interrupt service routine, and then the processor will jump to the interrupt routine and will now process the control logic. So as you can see, it is a long process, and as I said, this is going to be complicated, right? Even for me to actually design this lecture, it took quite a while, right? I had to make sure that I got this entire layer correctly. So there are several layers, from the peripheral to the PIE module, from the PIE module to the processor, and finally at the processor. These are the levels we have to go through. Again, if necessary, watch this video maybe 2 or 3 times. It is complicated, but make sure you understand this before you continue, right? Because interrupts are the soul of power electronic applications. You must understand how interrupts are set up, how they are serviced, how they work, right? So the next question you might be asking is, how is it going to find the interrupt service routine, right? And that is what I'm going to talk about in the next lecture. So again, take your time with this lecture. If you still have any doubts, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, I will see you in the next lecture. Thank you so much for listening and goodbye for now.